Good morning. Good morning, good afternoon, good evening to everyone. Welcome to the second day of the training on water pollution for the Copernicus Marine Service. I'm Florian Caillon, Training and Capacity Development Officer at Mercator Ocean International, and I'll be guiding you through this session. On Tuesday, we explored the Copernicus Marine Platform and got insights on how the data can be used to address water pollution. The replay of this session is available on the event website for anyone who missed it. Today, we're shifting from exploration to practice. This session is dedicated to hands-on demonstration using Python, QGIS, and R, all applied to real Copernicus Marine Service datasets related to water pollution. We encourage you to follow the demonstrations, ask questions, and use this time to interact with our speakers. You will have access to the full notebooks afterwards. Do you hear me well? Can you hear me?
Yes.
Okay, great. You heard all the introduction.
Yeah.
Okay, good. So you will have access to the full notebooks afterwards, so you can take your time to run them on your own, experiment and explore the workflows at your own pace, sorry. So let's dive in. Before we begin, let's quickly go over some house rules to make sure you enjoy this session to the fullest. Please don't use the chat box on your right-hand side for questions. It's there for greetings and for sharing links with participants throughout the sessions. If you have a technical or content-related question, we invite you to use the dedicated Q&A section on the website. It's at the top of your screen on the website. Simply click it to open the dedicated space where you can ask your questions to our speakers. We'll have a Q&A session at the end of each presentation. And while you're there, you'll also see a quick survey about today's webinar. Feel free to fill it out anytime during the session. Finally, we encourage you to visit the guidelines and resources section on the event website. There you'll find useful links to the materials and tools we'll discuss today. So now let's take a look at today's agenda. We have a series of exciting presentations and tutorials lined up for you. We'll start with a presentation of the Copernicus Marine Toolbox by Anaïs Perrin from the user support at Mercator Ocean, followed by a Python tutorial presented by Louise Balmas from Noveltis. And after a short coffee break, we'll dive into two other tutorials in QGIS and RStudio presented by Daria Andrievskaia and Simon Millet from Noveltis. Let's begin right away with the presentation of the Copernicus Marine Toolbox by Anaïs. Anaïs, the floor is yours.
Thank you, Florian. So I will share my screen first. Okay. So hello, everyone. My name is Anaïs, and I'm a part of the user support team at Copernicus Marine Service. Welcome to this presentation about the Copernicus Marine Toolbox, our official tool to access and download marine data from the Copernicus Marine Data Store. So the toolbox is free and designed to be easy to use. It lets you explore the catalog and metadata and then download either the original producer files or subset data, meaning only a region, time period, depth range, and variables you actually need, whether they come from numerical models, satellite observation, or in situ measurement. Key benefits is that the toolbox has no quota, neither on volume nor bandwidth. In other words, you can explore and download everything available in our catalog without quota limits. So during this presentation, I will summarize the main comments, then show you the related Help Center resources, and finally do a short live demo in both command line and Python. So the Copernicus Marine Toolbox has four main functions. The first one is the logging function. So this function creates an encrypted configuration file containing your credential so that you don't have to re-enter your username and password each time you want to download data. The second function is called describe. It allows you to retrieve catalogs information and details metadata for products and datasets. The third function is get function. This one lets you download the original files exactly as they are provided by the data producers. And finally, we have the subset function. This one is particularly useful if you want to extract only a part of the data, for example, a specific region defining a time period or selected depths. All these functions can be used in two different ways, either from command line interface, such as Miniforce prompt, or any other terminal, or directly from Python environments such as Jupyter Notebook, Visual Studio Code, Google Colab, or any other code editor. So before we go further, I would like to show you the Help Center collection dedicated to the Copernicus Marine Toolbox. So from the Help Center, here, go to Copernicus Marine Data Download, and then the Copernicus Marine Toolbox here. This is a collection of all Toolbox articles. You can still search using the search bar at the top. The collection is organized into 4 sections. The getting started cover the basics like introductions, installation, the executable option with no installation, credential configuration. The main functionality provide separate step-by-step articles for each command, both in CLI and Python. Use case gives useful scripts like recurring download, working from CSV point, depth selection, in situ index files, and much more. And finally, the troubleshooting and FAQs include, among other things, common issues and solutions, how to report an issue and request a feature, or the roadmap. If you get stuck after today, this collection is the best place to start. So now let's move on the practical demonstration, and I will start with the command line interface using Miniforce prompt. So I will open Miniforce here, like this. And the first step is to activate your Python environment, typing mamba activate. Here's CMT. I have named my environment CMT for Copernicus Marine Toolbox. Please note, I'm no longer in my base, but rather in my environment CMT. So to check the Toolbox version that is installed, you simply write Copernicus Marine version with 2 dash. And now the Toolbox here say that the current version in use is the latest stable version 2.2.5. So let's start with the describe command, which is used to explore the Copernicus Marine catalog and retrieve metadata as JSON. To see all available options, simply write Copernicus Marine describe -- help. And you will see on the left, like this, on the left, all the possible options, and on the right, their description. So for this demo, I want to quickly identify the product ID and the dataset ID relating to oxygen and keep the JSON easy to read. So I will run Copernicus Marine describe -C02. So -C corresponds to content option, which filters the catalog by returning entries whose metadata contains the word O2. So the search applies to all attributes in catalog. Then -R. The -R is for return fields option. It's for it keep all only the field we care about here. So it's a product ID and the dataset ID. So we can reuse the dataset ID later. And after, I will include the exclude file option, or just E for shortcut, in order to lighten the JSON and make it more readable during this live demonstration, such as the description, the sources, and the keywords. And finally, I simply save the JSON output to a file, which I will call O2 products.json. All right, so since the query is performed on the entire data catalog and I'm on live streaming, it's take a few moments. So now it's almost finished. All right, so when the process completes, I will open the JSON here in my CMT folder here. Oh, sorry, okay, sorry, I make a typo in my query. It's sources and not what I write here. Sorry for the wait. If I check the other file, it's empty, so I will delete it. Okay, so rewrite it, okay. Sorry for the wait. And now I will have, yes. So now, oh, sorry, I will open the JSON file with Firefox here for greater visibility of the output. So here's the output list. All the products and data sets are returned by the O2 metadata search. And I will come back to this JSON later. So now let us move to the logging function. So this function creates a secure identification file so that you don't need to type your credential each time. You only have to do this once. So the command is Copernicus marine, sorry for the typo, logging. So when you will then be asked for your username and then your password. And please note that the password is hidden as you type, and I will overwrite it. And when it's done, you can find your new identification file in the .copernicus marine folder at your default directory, and you retrieve here the .copernicus marine credential file. Okay, so now we will move on the get function. I will clean the screen. As a reminder, you can display your variable option by typing Copernicus marine get -- help. And the only mandatory parameter for this function is the dataset identifier here, or just I for short. I will reuse the dataset ID I found in our JSON file, and I will take this dataset, for example. Okay, so the simplest possible command look like this: Copernicus marine get I for the dataset, and then the dataset name. But I'm not going to run it like this because with that additional selection, it will download all the file in the dataset. So before downloading anything, I will quickly open the dataset page in the data store to check the time coverage of this dataset. So I will go to dataset data access tab here, and I can see the dataset and their time coverage, which helps me to choose a date that actually exists. So now let's say I want the file for the 1st June 2025. So here I'm selecting the right file by filtering on the file name using the filter option. So here I will enter filter and then add the date. So notice that the asterisk indicates that there may be other character before and after the date in the file name. If I want to choose where the file is saved, I can add O for the output directory option and indicate my folder. So by default, the Toolbox keeps the server's folder structure when downloading. So you get an organized directory tree. But if I prefer to save everything directly into my target folder, I can add the no directory option or just ND for short. And I launch my command. So when I launch the download, the Toolbox prints useful messages like the dataset version being retrieved, the dataset part, often default, and the download start. And I will retrieve my new file here in my data folder. So now let's switch to Python. So I'm going to start Jupyter Notebook in my computer directly from my CMT environment in Miniforge. I can do that because I previously installed Jupyter Notebook package inside the same environment. So from Miniforge prompt, I will run Jupyter Notebook like this. So this launch Jupyter locally. And now I can open a new notebook using the kernel associated to my Toolbox environment. Here, in my case, it's CMT. So to use the Toolbox in Python, I first import the package like this. So now let's look at the subset function. So this function lets you extract only the part of the dataset you are interested in based on time, area, depth, and variable you choose. If I want to check the variable option in Notebook, I can type here Copernicus marine dot subset, so the function's name, and add a question mark. And here I have the help option directly on the cell. So for this demo, I'm going back to the subset request I prepared during the Tuesday presentation in my Ocean viewer here. Instead of building the request manually, I will use the automate button. It's generate a correct Python template here so that I can copy and paste it directly into my notebook, which helps avoid mistakes. So then I will delete the import because I already do it. And then I will add two practical options. So the output directory and the output file name. So I control where I want to save my data file and what it's called. Here, subset and see. All right, so I retrieve the message here, the start download, and here I will check here in my data folder, I retrieve my subset netcdf file. So now let's look at two additional functions that they are only available in Python. It's open dataset and read data frame. The open data, the first one is open dataset. This is very similar in spirit to subset because you can provide the same kind of selection parameters in variables, time range, depth and area. But instead of downloading the file straight away, it opens an X-array dataset remotely. So this is great for exploring the dataset structure without downloading everything. So during this live demo, I will reuse the exact same selection in my as in my previous subset request to keep the small and responsive. And I will change the function here to open dataset. I will remove the output directory and output file name option because those functions don't apply to open dataset. And I will store the result in a variable called dataset, for example. Okay, dataset. And now Jupyter display the dataset through X-array. At this stage, it's not saved on my computer. If I want to write it to disk, I can export it at netcdf using toNetCDF function. And that's the moment where the data transfer and computation actually happen. So I can simply write dataset.toNetCDF function and then specify the path to the folder and give a name of my new data file. And here I retrieve my new file name. So the second function is the read data frame. So instead of returning an X-array dataset, it loads the result into pandas data frame, which is handy when you want a table-like view and when you plan to export to CSV. Important note, so pandas load the data into memory. So if you request too much data, you hit RAM limits. That's why it's usually best to keep the request small or subset first. So I will reuse the same selection again here and replace the function by read data frame. And I will store it in a variable named data frame. So now I have the data display as a pandas data frame, so I can expect it in a familiar table format. If I want to save it as a CSV file, I can do the same as a toNetCDF function by using the toCSV function. So I will indicate the variable data frame, and then the toCSV function indicate the path of my folder and save the data in CSV format. And now I can confirm the CSV is not available in my data folder. So that's it for the overview of the Toolbox function I want to show you today. One important note, not all datasets in the catalog are available through subset service yet. The good news is that even when the dataset is still being integrated into subsetting, it's remaining fully accessible via GET, so you can always download the original files. To check the current status, so I will go back to the website and open the user notification service in the user corner here. And this is where we publish operational updates regarding products. In the incidents category, you can find the notification titled Dataset in progress of being formatted for the service subset. which lists here the dataset for which subset is not yet available. We update the notification as soon as the dataset becomes available. And of course, if you run into an issue, you can resolve with the Help Center or our AI assistant Blue. You can always contact our user support via the chat widget here. Thank you all for your attention.
Thank you, Anaïs, for the presentation of the toolbox. I will start sharing my screen again. Before we move on to the next speaker, we want to make this session as interactive as possible. So if you have any question, we'd like to hear from you. It's really easy. As I said, just click on the Q&A tab on the event website or scan this QR code with your phone and type in your question. We'll be collecting your questions throughout the session and addressing them during the Q&A. So don't hesitate. Your inputs help us make this discussion even richer. We also invite you to share your feedback on today's webinar. You can complete the survey available in the Q&A tab also on the event page. So now let's dive into the question for Anaïs. I'll start sharing my other screen. Here. Do you see it?
Yeah.
Yes, okay. So for the first question, someone said, we're investigating marine mucilage and would like to know whether Copernicus tools could support us in oxygen levels and nutrients in the Mediterranean.
So you can search for your product or data of interest in directly on the catalog or ask Blue. But I don't have the knowledge of the full catalog and a lot information about the product itself. So I can directly answer your question, but we have our AI assistant Blue, who is trained to answer this kind of question.
Okay, thank you. Someone asked, can you use get function also in Jupyter Notebook and not only in the command line?
So the get function can be used in command line and on Python, but also in other programming languages. You can consult the Help Center to see all the articles about our different function.
Okay. Is there an option in the catalog query to say if a coordinate is in the ocean or not? Like if the coordinate is available as an ocean data point?
In catalog query to say its coordinate is in ocean or not. So when when you are in land, most of time you have the noun values, but you also have for some product the MASH or the statics file for the bathymetry, and then you have the mask of the land and sea, and you can have this kind of information with this data file.
Okay, nice. How can deep ocean currents be calculated, and does a direct product exist?
You have to inspect the product documentation because each product are different and their assimilating modes are different. So deep ocean currents. So yeah, it's it's very particular for each product.
Okay. When selecting dataset, can we do SQL queries direct to Copernicus Marine Service?
No, for the moment, we can't apply a SQL query at my knowledge. So, no.
Is it possible to download the product monthly?
Yeah, of course. You have some monthly data sets or daily data sets or yearly data set, and you can also consult the article recurring in our center, recurring data. So you can apply a script to automatically download a time period of over years and months. And so, yes, it's possible.
Nice, I can help for research. The next question is, do we have to get Copernicus DS for operating with data, like large downloads?
I don't know how to answer this question right now. So please contact the support, and Blue or one of the agent will take the time to look into it.
And finally, our last question is, when saving your data, an error sometimes appears on Windows if you don't make the path raw, unlike on a Mac. What do you recommend?
Saving the data, an error message on Windows. I don't have I don't search for this. I don't know for the moment. No, I don't know. Sorry for the moment, but we can search for correct this output, and I will consult my member team to answer the question.
Nice, thank you.
Sorry.
Thank you, Anaïs, for your presentation and for the presentation of the toolbox and for answering the questions. We will now move on to our next speaker,
Thank you.
who is Louise Balmas, who will present a Python tutorial. So Louise, the floor is yours.
Thank you, Florian. Hi, everyone. So today I will present you a Python tutorial about the water pollution. So I will share my screen. Okay, can you see it?
Yes.
Perfect. Okay, so welcome to this Copernicus Marine training session on water pollution with this Jupyter notebook. Today we will focus on simulating the trajectory of pollution in the Mediterranean Sea. First, if the kernel is not working for any reason, you can refresh with the button. It's hidden under my here, and you will execute each cell through the play button. So to introduce this topic in the current context, in order to protect the environment and ensure safety, it has become essential to understand how pollutants move and evolve in the ocean. And the Mediterranean Sea is heavily affected by maritime traffic and coastal development. So it is particularly exposed to pollution events such as oil spills and plastic debris, for example. And in this tutorial, we will simulate a simplified pollutant trajectory in the Mediterranean Sea using CMEMS ocean current data. And we will visualize transport pathways and compare the results with drifting buoy observations to evaluate our model and illustrate the main factors that control pollutant dispersion in this highly dynamic region. Our Jupyter notebook runs on Python, and here are the libraries we'll be using. So there is the NumPy package for scientific computing, Pandas to manage with data tables, Xarray, very useful to manipulate netcdf files, Matplotlib and Cartopy for plotting, and datetime to manipulate dates and time. So first, you will have to run this cell to import the different libraries we need. And then let's talk about the data. We'll work with two different types of data. First, the model data, extracted from the Mediterranean Sea Physics Analysis and Forecast from Siemens, and the in situ data to evaluate our model. So the trajectory of a drifting buoy in the Mediterranean Sea. And those data sets are provided in netcdf format. It's designed for storing multidimensional scientific data and very useful for such studies. First, the model product, the Mediterranean Sea Physics Analysis and Forecast. So we'll retrieve daily surface currents from this product. The product identifier is this one. And if you click here, you will have this page, and you can find the ID you want with here. Here we use the daily currents, but you can also try to retrieve the monthly, hourly, and many others. And the product we will use has a spatial resolution of approximately 4 kilometers. The variables that we'll be using are the zonal current and the meridional currents, and the temporal resolution, as I said, is the daily one. So if you want more information on how to use the product, you can consult the product user manual. And if you want information about the quality, you can visit this document. And concerning the in situ data sets, the drifting buoy trajectory, you will find it following this link with this ID. And how to access the data with the Copernicus Toolbox. I will not enter in detail in the Copernicus Marine Toolbox as it was presented before, but it's the library that can be used to download Siemens data from Python code. And first, we have to import the toolbox. So to run this cell, then this one with the login, and you'll have to enter your credentials. And as a start, we use the daily currents over in the entire Mediterranean basin. We have to define the area, the desired area. So let's fix this and define a time range. So we decided to use a quite recent period. So from the end of September to the end of October. And to get the currents data, you have to run this cell. This is the ID that we saw on the web, the Copernicus Marine page. The variables we are interested in, so U0 and V0. Here we fix the depth we use. We fix the minimum and maximum at the same depth because we would like to have only the surface current. So this is the minimum depth we can find here. And create the output current. So it will be created automatically if it's not already created. So here it will goes here. Okay, so let's have a look at first look at our current data. Here is the command to open our data sets. You have to make sure that the path corresponds to the location of your initiative file. And to visualize the dataset structure, you have to write this. Then this information will appear. You can find the coordinates, time, longitude, and latitude, also depth, but it's empty as we only selected one depth. The variables that we wanted, U0 and V0, and some other attributes. You can visualize the values by clicking here, and you will have all the values, and some other metadata here. Now let's explore the data sets. To visualize it to plot it on a figure, we can, for example, decide to average, to calculate the average along the time dimension, and to plot a figure with the mean surface currents over the selected period. So to do so, you will have to use the mean function. And let's plot the new data set, average along the time dimension. So here, the time is no longer coordinates, and we still have our variables U0 and V0. And let's plot this data on a figure. So we'll use those functions from the matplotlib library, the figure axis, set, extend, add features. Everything here is for the background. And if, for example, if we want the mean current in color on the background and the direction represented with quivers, we can use this. So preparing the quiver, associated coordinates, the current speed here, the current velocity, and the color for the current velocity map. And if you run this cell, you have this figure, so the current velocity and the quiver. And so this is average currents field over the selected period from the end of September to the end of October. And there are clear patterns that are displayed, for example, here and here. So we guess that there are strong currents over this period. And now let's use those currents data. We visualize them, but let's see a concrete example how to use them, how it can be useful in a study. So let's, for example, imagine a worst case scenario. What would happen if an industrial pollutant is spilled into the port of Genoa in Italy? So this is an example on September 22. And where could the waste have been found 6 weeks later at the end of the selected period on October 31st? So we'll create the initial point location, so the Genoa port location. Here we have to set a number of particles. So here I choose 200, and the size of the initial area of the particle distribution around the selected point. Then we will generate the simulated particles around this position. So using this cell that generate random particles around the center points. Then when we have the position list, we will plot them on a map. If we here, there will be two figures. First, a figure with presenting the initial point location on the area, and a zoom. And if you run this cell, you will have those two figures. So the first one showing the initial point location, and the second one with the point distribution. So a zoom in the first figure. So now we have our initial points, but what we want is to make them move, and make them move according to the current data that we retrieved. So to simulate the movement of these pollution points, we'll define a function that calculates the sequence of positions for each point created to obtain trajectories over the period. So this is the function, the simulating particles function. The parameters that we need to enter are the first DTS, the data sets. So the currents with U0, V0, longitude, latitude. So our current data. Long zero, lat zero are the initial, the central longitude and latitude around which our simulated particles are initially distributed. The number of particles we selected and the spread number. And it will return a tuple of positions that we will be able to plot on a map afterwards. So first we create an empty list of positions. And then we generate random particles around a center point, and it's the same. These are the same lines as previously presented in the previous function. So we calculate the time steps, a landmass. It is important to define, to constrain the trajectories of the points in order not to make the point continue on land. Defining a function that allows to find the index of the array elements whose value is closest to the required value. And calculation for each day. So we update every day the new position, and making sure that the landmass is also applied. And the displacement chosen is a simple Euler displacement with the new position equal to old position plus velocity multiplied by time. And after that, we will have, it will return the position list with tuples of particle long and particle latitude. If we run this function, so we retrieve this position list, then we would like to plot it on a figure. So same structure as before to plot them on a map. And if you run the cell, you will have those two figures. So first with the initial position as previously seen, and the simulated point trajectories with the 1 point for 1 day according to the currents over the selected period. And it seems to coincide with the strong current that we visualized with the mean map before. And now it could be interesting to visualize the currents that make those particles move, because here we only visualize the results, but we can, for example, superimpose the currents, the map of the currents with the trajectories. And to do so, we can, for example, create an animated function that will allow us to create a dynamic animation to visualize the movement of the points under the currents that drive them. So this is the animate particles function that will take the data sets and the positions list created before. This is so to prepare the figure, same as previously. If we want the quiver to visualize the current's direction, we'll fix them, set up them like this. To have the color map for the current's velocity, we'll use also P color mesh, color bar, as before. To build the quiver function, we have to initialize the points, and then the update function that will update positions day by day. And then it will return this animated function. So to call it, you have to run this cell and this animation will appear. So I will just launch it. And then we can see the particles' trajectories according to the currents that drive them day by day. So we are, okay, we were at the end of our simulation. I will just stop when it's over to visualize. Okay, and so here it corresponds to the previous figure here with the trajectories. So the movement of the points coincides with the currents we retrieved, and these superimpositions is useful to better understand the trajectories observed. And we can see that some of the particles are heading towards the Gulf of Lion, and others are going back to Corsica. And in 6 weeks, the area affected by pollutants is significant, because one grid cell here is approximately 122 kilometers, so they travel more than 300 kilometers in only 6 weeks. And now we would like to evaluate the accuracy of our model. And to do so, we will use the drifting buoy in situ data mentioned before to compare to the model outputs. So to get the in situ data, you have to follow this link, and the ID to search is this one. It's not, yes, okay. You will find it here. It's not an automatical downloading as for the current data, but you can easily find them with this ID. To visualize the structure of this in situ data set, it will be the same as before. You just have to mention here the time you want to visualize, because when you will retrieve the data, it will download all the available data set. And then, so when visualizing the data set, you have the same structure, the coordinates, and here we are only interested in the time and the position of the buoy. And then let's plot, let's display those positions, the buoy positions between September 22 and October 31st, sorry. So to plot it on a figure, same block as before, with the function set extent, add feature, gray lines for the background, and scatter to plot positions. If you want to have trajectories, it's better to use plot. And then you will have this. To have, sorry, I forgot to mention this. If you want to highlight the buoy start and the buoy end, you can mention to have specific points, so the first one and the last one in different colors, as shown here. So the buoy start here and the buoy end here. So this buoy is located northeast Corsica, first on the 22 September, and it's drifting in the Tyrrhenian Sea, and its course at the end of October here. So if you remember, there was a gyre here that was highlighted by the mean currents. We can see, we can go back to the section, 3.4 to visualize it here. And the drifting buoy seems to follow this gyre, but we will check this later. So let's go back to our in situ data. And now we have our in situ data. We can plot its trajectory, and it seems to be to coincide with our current data. And let's see if our simulation is relevant, and evaluate it against this in situ buoys. First, the trajectories. In situ compared to the simulated one. We have to set a new starting point that is the same as the boys' starting points. And I choose not to change the number of particles and the spring number. We have to call our simulating particles function to have the positions of the particles according to this new initial position. And once we have our particle position list, we can display it, these positions on a map superimposed on the buoy trajectory with same block to visualize. And here, so scatter as well, plot as well, these are the same as before. We can just here choose to have different line style to visualize the trajectory particles. So these are just to have to make the map more understandable. And you will have this, the simulated trajectories and the in situ buoy with the buoy start and the buoy end. And our model outputs seems to follow the buoy very closely, but only on the first part of the simulation, because after in the middle of the period, the simulated particles tend to return towards the Italian coast instead of continuing the gyre that the buoy is following. But let's have a look at the currents to understand those trajectories, and we can do the same as before with our animated simulation. So this is the animate particles too, as the same function as before. I just add 2 lines to add the buoy trajectory on the animated simulation. So this line and this one inside the update function. And if you run this cell and call this one, you will have the simulation with, in blue, the drifting buoy and our simulated particles. We can see that it followed the gyre, and our particles are going back towards the Italian coast, but we can see that there is as well a strong current here. So it's, yeah, our simulated trajectories are coherent, and they have allowed us to understand how to create a meaningful model in a very simple way using data available from CMIMS, because it is important to know that we have built a very simplified model here, which only accounts for the effect of currents, but there are many other factors that come into play in a full drift model. So if you want to go further, these are some examples of further exercises. In section 4, for example, we animated a current field over a specific period, but you can explore more by changing the starting date and starting point. You can also vary the number of particles and the extent of the initial area of the particle distribution. And if you want to go even further, you can try to change the area of interest of the retrieved data set and reproduce the analysis connected here. And you can even choose another region elsewhere than in the Mediterranean Sea. And here, as I mentioned, it's a very simple drift model. But if you want to add new effects, you can improve the model with, for example, tide effects or wind effects and many others. So congratulations and thank you for your attention. Here you have learned how to access CMIMS data with the toolbox, how to visualize data such as current data, how to create a simple model of water pollution trajectory. You learn how to visualize in situ data and how to compare a simulation with those in situ trajectory. So I hope you enjoy this chapter journal notebook. And if you have any question, you can contact yes, we'll have a question session just after that, but you can also contact the support here. So thank you.
Thank you, Louise, for your presentation. You will be able to download the notebook from the event website. Let's go through your Q&A. And for any questions that we don't have time to answer today, you'll be able to receive a post-event report where we can go a bit deeper in the questions that we did not have time to address. So for the first question, how many ports Copernicus has enlisted on a weekly basis, I guess? And there's a second question that say, how can I generate a list of them based on your data?
Okay, so I don't know the exact number of ports that Copernicus has enlisted, but you can. I invite you to visit the Copernicus Marine website. You will have access to all the products that you can download, and you can easily generate a list once you have you are on the page of the data access.
Thank you. Has the approach that you presented been applied to assess pollution in a river, for example, in the context of the Congo River?
I think it's completely possible to apply such a study in another context, for example, in a river. But I didn't study this specific case of study, but if you have current data available in this region, it's completely possible to reproduce the same study.
Thank you. Can this pollution workflow be replicated for inland waters, like lakes and rivers?
So yes, it's the same point. If you have once you have current data over somewhere, you can find it. But in lakes and maybe the current data are not as strong enough, but it depends on the area. And here it's a very simple model with the earlier displacement, so calculating the position with just the current positions. So it can be applied wherever you have current data available.
Nice. This question, oh, okay. When adding wind data to the ocean model, do I need to regrid the wind data first if the resolution doesn't match?
Yes, probably. It can be easier to regrid the wind data to make them coincide with the current data to simplify the model. But I think there are many different ways to adapt the code.
Nice. Yeah, so for this question I can answer. It's a nice reminder to say that the notebooks, the Python notebook, will be available on the event website on the top tabs. You can reach all the documents if you want to follow them after today. For our next question, already thank you very much for the presentation. I was getting to this point later on. Someone asks if Copernicus is providing data regarding previous events like oil spills.
So first, thank you. I don't know if previous events were talking about oil spill, but maybe a Copernicus expert will have a more precise answer about this.
Thank you. How can I develop my skill of coding to work with marine data as a learner?
Good question. So I think that you will improve your coding skill step by step when you are facing a situation. If you want to visualize some marine data, and I think I don't know how to give a precise way to follow it, but if we need functions here, even here to create this Jupyter notebook, we learn new function. If we need a specific a tool, if we need a specific function, it's, yeah, you will improve step by step.
Yeah, by following the tutorials, this one or also the ones we developed for previous events that you will find on the Copernicus Marine website.
Exactly.
You'll be able to step by step become better at coding. For the next question, for waters with strong tides, is daily mean current data sufficient, or should I use hourly data to prevent errors?
For waters with strong tides, I don't know. Maybe you can try both. Maybe the hourly data would be, for sure, it will be more precise if it's not too heavy to download. Yeah, but yeah, let's try.
There's a linked question. The next one is that the model moves particles in 24-hour step. For example, in narrow straits, won't this cause particles to accidentally, jump over small islands?
Yeah, with the land mask presently mentioned, normally it fixes this, but in this specific case, we didn't have this problem. But yeah, I think we have to study this specific point. Once your land mask is strong enough, normally you won't have those problems. But yeah, it depends on the precise situations.
Thank you for your answer. And for the last question, in terms of resolution, if you would have added more red points, do you think it would have followed the buoy more?
Honestly, I don't know, because I think the fact that it's not exactly following the buoy can also be the other effects that we were not that we didn't take into account could be responsible for this small for the fact that it's not perfectly following the buoy. But yeah, I think the you can play with this number of particles, initial number of particles, to see what are the effects, and if they are just more following the way that the simulation is following. But if some of them are taking the buoy's way, yeah, I think these are things that you can explore.
Nice. Thank you again, Louise, for your presentation.
Thank you.
We will have now a short coffee break, and we'll be back at 11:15 for 2 new presentations, one on tutorials on R and one tutorial in QGIS. So stay tuned and see you in a few minutes. Welcome back, everyone, to today's session on water pollution. We will keep going with the agenda, with the presentation from wait, I'm going to share the good screen. From the presentation of a QGIS tutorial from Daria Andrievskaia. Daria, the floor is yours.
Hello, thank you, Florian. And well, hello, everyone. I'm Daria, I'm work at Novelties, and today I'm here to present you the QGIS tutorial, which is dedicated to study of a dead zone in the Gulf of Mexico. I am gonna share my screen. Okay. Do you see my screen?
Yes.
Okay, great. So first, before we move specifically to the exercise itself, I'm gonna talk a bit about the context of a problem we're gonna study, and also show you the product we use from Copernicus Marine Service. So as we're gonna talk about the so-called dead zone in the Gulf of Mexico, so the dead zone is basically, well, here you can see a beautiful image I found in the internet of how the dead zone forms. So basically the dead zone is a zone with a very low oxygen concentration in water. and it usually forms in warmer seasons. For example, in the Gulf of Mexico specifically, it forms each summer, and it forms under the input from the rivers, so fresh river water, which also brings the different chemicals from the ground. And here in the Gulf of Mexico, we have Mississippi River, very big, very important river that brings a lot of chemicals into the Gulf. And basically, this input of the chemicals feeds the algae, and while they bloom, they start to grow massively, and then they die and they decompose, and this decomposition, it consumes oxygen. So basically it depletes the seawater from oxygen, and slowly the water becomes oxygen deprived, and of course it harms marine species, because we need oxygen to survive. And this dead zone occurs, and fish and other marine species, they usually migrate. Well, if they weren't very fast enough, they die. And mostly it affects the marine species that live on a seabed or close to the seabed, so like crabs, shrimps, and all those small things. And they usually don't have time nor ability to kind of escape this dead zone, and they just die. So that's a very big problem that hits this particular zone for the marine habitat and also for the fisheries. So for us as well, because we benefit from the fish production. So that's what we're gonna study. And just for information, also this zone is very well monitored to see how the dead zone evolves during the from year to year. So as I told you, we're going to use a product from Copernicus Marine Service, and that's a global ocean biogeochemistry analysis and forecast. And from it, we will use 3 variables. It's concentration of chlorophyll in seawater, it's dissolved oxygen in the seawater also, and nitrate in seawater. Because, we want to see the oxygen because it's even it's depleted of oxygen, that's the dead zone. We want to see nitrate because that's the input from the Mississippi River, and also chlorophyll to spot the bloom. So we're gonna use daily mean data, and we're gonna focus on period of time from June to August in 2023, just one of the summers, and we'll see how it evolves. So in the QGIS, I'm not gonna do a step-by-step procedure very in details, because I don't have much time for it, because QGIS takes quite some time. I'll show you the project that I already did, and if you want to have more details on the procedure, you can have a look at the PDF version of this tutorial, as well as a recorded video, which will be available, or maybe already available, on the event page. So let's start. And the first thing that we did to see what's happening in the Gulf of Mexico here is to actually spot this this chemical input in the Gulf. So for that, we plotted nitrate concentration, which is NO3 here, and just a little note to add actually the data from Copernicus Marine Service, which is in NetCDF format. We use a plugin which is called SMEM-NetCDF, and this is plugin which was developed here at Novelties, and it works with QGIS up to 3.30 version, and later versions might not work very well, so it's up to you. You can use this plugin or not. Well, for now it's not maintained with updates, but it is quite useful for working with NetCDF files in earlier versions of QGIS. So we plotted those time frames, and as I told you, we use daily mean, and that's a lot of layers if we take all of summer 2023. So we plotted only each 15 days, so 1st June, 15th of June, and so on until 30th of August. And Here you can see, if you double click on the layer, you can go to symbology and see the style, because when you add your information, your data to the QGIS, it adds, it assigns the style automatically or randomly. And here you can actually play around and have a better representation of what you want to see. And we chose these colors, we chose this color ramp to see very exactly the nitrates are the highest. And you can see that you have a blue and greenish kind of color. That's the concentration is at its max. And that was in June, 1st of June, and then we will untick a box to see the progression. So here it's a 15th of June, and you see that it increased. And then on 30th of June, you also can see that it started to move a bit with the currents a bit more deeper in the Gulf. Here it moves towards Florida, and you can see like that a little evolution of how it spread. And most important thing that we notice is, of course, that here in this zone, it's a very high concentration, like it's very very focused on there. And that's exactly the reason, that's exactly the place where we have a Mississippi River. It's coming somewhere here, we will see later also. So that basically shows us, yes, exactly the highest nitrate concentration in the Gulf exists, especially in this zone, because of river input. You also can maybe notice that it was quite high, well, it was lower in June, it increased through the end of June, July, and then late August, we kind of see that it's diminishing in quantity, like ozone it's covered. But of course, if we want to have more conclusions, we would need to load more data from our dates, yeah, from like September, to see how it progresses further. So now we spotted our input of fresh water and chemicals, and now let's see the other data, other variable we downloaded, and that's a chlorophyll concentration. Here we used another color ramp, which is greens. Well, it represents the best chlorophyll, and you can see that in dark green we have the biggest concentration. And again, it corresponds well with the zone which we initially spotted. So along the coast of Louisiana, and the Mississippi River comes into the Gulf. So if we look through the dates, you see that it kind of reduced here, kind of increased here, again reduced, stayed more or less the same, and then starts to fade. So basically we see this fluctuation of chlorophyll from quite like high values, let's say, to less high, and then it just fluctuates. And again, we see it's kind of reducing towards the end of summer as well. And that tells us exactly what as I told you for the dead zone, that that's basically the initial response of of ecosystem, because when we during the early summer, this nutrient, it supplies the alga with food, let's say, right? So it starts to grow, and then we can see fluctuations. So there are some naturally driven changes, and then by August, especially by late August, like as you see now, it starts to decrease gradually. Because by that time the algae starts to die, start to decompose. So that's also coherent. And the last variable that we're going to look at today is an oxygen. Very important note I didn't say, that is, here you can see on a layer, you can see the date for each layer, and also this little value here is 0.49 for chlorophyll and nitrate, and for oxygen it's 2160, and that's a depth because we have the products available at Copernicus Marine Service website platform. They have depth as a dimension. And we looked at nitrate and chlorophyll on the surface, because when the fresh water comes into the Gulf, it comes on a surface level, and then it starts to mix slowly. But usually it doesn't mix very deeply, especially on a coast. And same with chlorophyll. We needed to see the algal bloom, because it usually starts on the surface level. So that's why we chose this depth. And for the oxygen, we chose 21 meters, which is more deep. And this one, for example, when we activate it, we can see also that it does not correspond exactly to the same range here with chlorophyll, for example, because, well, it means that it's not that deep there. Like the coast, it's like less, it's more shallow. And we wanted just to see more like the lower part of the ocean, to see how the hypoxia occurs there. So the dissolved oxygen is decreasing near the seabed. So that's why we look at different depth. And here, like, let me deactivate it. So we also changed the style here, just look how it looks like. And yes, we have a higher oxygen with some more like orange color, and well, lower oxygen with more purplish colors. And if we look through the dates, what we can see that we would expect, as we said, to have low oxygen at the same place where we have a high nitrates and high chlorophyll. But here we can actually see that it's quite high still, and it remains relatively oxygenated, the water. And that might be, first of all, the process of decomposing of algae to deplete the ocean from oxygen. It did not start yet. And you can see that, well, generally with time, we can see that the ocean gets more and more less oxygenated. You can see it's more purple everywhere, especially in as well in a coast, kind of close to the coast, even though it still remains quite with quite high oxygen concentration. But here, for example, no. And of course, we can see bigger variation, not like lower, the opposite, yeah, lower variation in a deep kind of place of a Gulf. And that occurs because denser ocean water that intrudes into the shelf from, well, here from the ocean. And it's and also there's a stratification also which is involved, and that limits the mixing of water. So during summer, with the decomposition of organic matter from nutrient fueled phytoplankton, algal bloom, it reduces oxygen at depth and produces this characteristic zone, quite low oxygen. But as we saw that it is slowly reducing the oxygen, just not that drastically, as dramatically as we would expect. So that is for this variable. And what's next we wanted to do is to make a classification, which we call a hotspot classification, and which is basically this layer that I've created. And so what we wanted to do is to see the zones in which all these three variables, they correspond together, kinda. So we wanted to see the zones which are have, for example, here you have 4 different colors, right? So the zones in which there's no then all variables are low, let's say, they are not presenting any danger. So for example, here those pixels are not colored at all, so they're transparent. The ones that are showing, I'll show you like this, but yeah, the class. The ones that correspond all three of them. So for example, this low oxygen, sorry, high chlorophyll and high nitrate is in red. The green is only high nitrate, sorry, and then purple it's a high what's left? Chlorophyll, yes. And for this we use a raster calculator function here. And what we used is basically this little formula. I'll show you, just copy paste like that, it's going to be faster. It looks like that. So basically, we wanted to spot the zones in which chlorophyll is bigger than this specific threshold. That threshold kind of recommended, let's say, for the spotting such places. And we multiplied by 1 to say that's a class 1, assign it to the first one. Here, the nitrate is this one, and multiplied by 2, meaning that it's going to be second class. And if they're both are high together, then it's going to be third class here, which is in red, and we run it and we have this one. And yes, I actually said that there's also oxygen, but we did not add oxygen because it's going to be just too complicated, so we didn't add it to the computation. And what we want to do is just to have this two variables classification and overlay it with our oxygen on the 30th of July, I think we used, because also for this classification layer we used only one date, so to make it easier it was 30th of July because it's just middle of the season. And if we correlate it together, we will see also that here, like in green, you can see that usually it represents the high nitrate concentration, and you can see that it corresponds to, like with color, corresponds to higher higher oxygen here, and also same kind of correlation here in red. This is where chlorophyll and nitrate are high together. You can see that there's also corresponds to high oxygen. So basically such, that's very quick, I don't have much time, but the thing is that such layers, such classification layers allow us to kind of find the hotspots, zones which correspond to some specific conditions that we want to spot. So that's it with this exercise. And the next exercise, very quickly, was profiles. Yes. So there's a so-called profile tool, which is a plugin. It's usually default in QGIS, but sometimes you might not have it. So you would need to go to plugins, manage and install plugins here. And here you can find it here and upgrade it or install it if it's not installed. So the point of this plugin is to see the evolution more like in graphical way, not the visual like we see here with beautiful colors. And for that, we can just draw a line from the coast to, I don't know, like this, for example. Double click. We have a line, and now what we want to see is we want to see the very how the variables are changing alongside this line. So for that, in this window, you would need to choose, for example, we choose 30th of July oxygen. We add layer here, and we do the same with chlorophyll and nitrate, and it plots us the different lines, and it's not very representative because we all have different scales. So for example, we just remove the other two variables, we leave only oxygen, we reset view, and we can see how it moves, how it changes, and also like when you move a cursor, you can also see how it changes along the line, and you can see the correlation, the graphical representation of how oxygen moving away from the coast kind of dropped. It had some spike of this because the nitrate concentration was quite high at this day at this place, and then went down again. So if we look at the chlorophyll, we will see, we see the tendency of, let me do this very quickly. You can see the tendency that it reduces before we go away from the place where Mississippi River enters the Gulf. And we will see kind of the same for the nitrate as well. You can see that it also slowly decreases. And you can save the image as PNG, for example, but it will be very simple graph. So if you need some more information, you would need to adjust it with some external tool. And very quick last exercise is that we looked at the external layer of rivers and streams of USA, and we found it. Well, the information is given in the PDF file. I will not stop there. And that's basically a vector layer representing the whole Mississippi River here, which is actually composed of small parts, small lines. You can see that it actually crosses the whole country, so no surprise it brings so much input, chemical input in the Gulf of Mexico. And we also, if we right click and go to open attribute table, you can see that it's consists of several little lines that have a different length. And here you can see a little spoiler of the total length, and that was last quick exercise, is to calculate this total length to just see what's the length of it in kilometers, and it's 3,800 kilometers, which is a very long river, and it's also corresponding to the true data. And to calculate this, we used this miles column here. So basically summed it all, and for that we went to calculator, where it's like field calculator. And here basically in this tool you can add I don't know, you can add whatever you want, another column with sum or mean, or it could be much, like many possible formulas you can use. And what we used, I will just copy paste it again, is this expression, which is aggregating here from the layer which we use. It aggregates the sum, so it calculates the sum of the column miles. And since it's miles and you want it in kilometers, we multiplied it by 1.6. And then we run it. I'm not going to run it. And that's going to be total length of our Mississippi River. So that's it. I don't think I have more time, so I'm done. And I am ready to answer your questions. And yeah, I'm sorry it was a bit hectic and quite quick. So
Thank you, Daria, for your presentation, for this interesting tutorials on QGIS. I'm gonna share.
yeah, I'll stop sharing my screen.
The questions. The first question we have is, can you please show us how to download the data? So this is not today's focus, but we will put in the chat the help center link so that explains step by step how to download data. The next question is, how is it possible to obtain this expression?
I assume the person wants to know the expression that we used for the different calculations.
I assume.
Yeah, and all the formulas, they are given in a PDF file, which is available on the website. So you can just go there and copy paste it and use it for your own analysis.
Nice. Can resolution be improved when viewing nearshore areas in QGIS?
Well, for the data we have on Copernicus Marine Service, you have a specific resolution, and well, you cannot change that. But of course, in QGIS and also like in Python, I assume you can. What you can do is you can extrapolate, right? You can just choose the zone and say, well, I have those pixels, like I don't know, you have 4 pixels, and you use different methods to basically make 8, I don't know, pixels out of 4. So it's going to be mathematic, right? So it's going to be modeling, but that's the only solution. Or maybe you can find more precise resolution data as well. But yeah.
What is the specific depth that you selected for this pollution data analysis? And the second question, what is the ideal depth for accurately studying sea surface pollution?
So for that, I think I mentioned it, but yeah, we chose for chlorophyll and nitrate, it was a surface level. And for oxygen, it was at 21 meters deep. So what is the ideal depth for? Boom. That really depends on what exactly you want to study in the seawater pollution. Like, well, it's surface pollution, but not surface level is ideal. But it depends on the variable, because, for example, as I told you, nitrate, when it arrives at the Gulf, it will stay mostly on a surface level, or it will go a bit deeper, but it's not going to mix that much. It's going to be just spread it very far away, very quickly, let's say, and well, just diluted. And but for oxygen, since as I said, it's very important to see what happens closer to the seabed. For example, you need to choose a depth that's the closest to the bottom. And yeah, it really depends on your zone and on your application.
Okay, thank you. Someone thanks you for your presentation and asks, can we use any version of Quantum GIS?
Usually, yes, you can use any supported official version. I just mentioned the plugin that allows us to map those variables from netcd files, and as I told you, yeah, from specific versions, it just doesn't work very nicely, we can say. But there's also like default function of adding the netcd, like of working with netcd files in QGIS, so it's not a problem. So you can use any version.
Okay, nice. Is it possible to use this data for El Nino and La Nina effects?
Well, I don't know what exactly you want to study in those phenomena like El Nino and La Nina. Maybe there are different variables you want to see, but yeah, of course, I mean, this data is, if it's applicable to the study you want to perform, yeah, of course.
Thank you for your answer. Quickly question for GIS. What is the name of the plugins to add? I don't know if you mentioned them.
Yes, and again, like in PDF file, you can have a full names if you want to note it later. So the one that's used for mapping, for adding the data, the layers to the QGIS is it's MEMS-NITS-CDF, it's called, and there is a link to it in the PDF file as well. It's available on the Copernicus Marine Service website. And the second one I used is called Profile Tool. It's called Profile Tool, and it's usually default, but sometimes it's not.
Okay, nice. And again, on the plugin, is there an alternative to use for newer version of QGIS?
You can just use I tried with 3.40 in QGIS, and it did work. It gave me errors, like it showed me error messages, but it's still plotted. So I don't know why. What was it not content with Adenate? But if you don't want to have problems with this plugin, you can just use like default function of QGIS to add layers. You will just go to Layers tab, you click on it, it's add layers, add raster layers, and you will just use your netcd file. The only thing is that it's not, yeah, because you have several time frames in the same netcd file. It might not I think it will add it like one layer, and to change the time frame, you would need to change a band in it, like it's multi-band image kind of. So yeah, I think that's most inconvenient thing out of this default function of QGIS.
Okay, nice. Can we use AHP method to make the classification for those parameters?
I am not sure I'm aware what AHP method is, so I cannot really answer this question right now.
I cannot really help. But yeah, if there is any unanswered question, we will answer them in the post-event report that you will receive after this session. And yes, we are reaching the end of the Q&A session, but we'll have time for the two next. How can we finalize the dead zone? Not sure what that means.
I guess maybe it means just like, what's the conclusion? I think that's what they wanted to say. Well, it is much harder to have a clear conclusion based on what we saw, because, well, the best one would be to apply, well, to look at more dates, to look maybe not each 15 days, but a bit more frequently. Also, what can be added to see more evolution, more like precisely, is to see deeper levels for oxygen as well, for oxygen concentration, and also to see what's happening in September, for example. All of that is also stated in a PDF file as additional exercises for you to continue working on if you want to deepen your knowledge with the data and QGIS. So the thing is that what we wanted to see is that, yeah, the chlorophyll does increase with the nitrate high concentrations, which is true. And we saw also that slowly this part of ocean, well, in the Gulf, the dissolved oxygen decreases, but it's also not only because of the zone, because the zone is very, very local. It's very close to the shore. And it's also the consequences of, well, deep water mixing of the ocean, which brings fresh cold water, which is also lower in oxygen. So yeah.
Okay, nice. Thank you. And for the last question, is the NetCDF plugin you used available for ArcGIS Pro? And if not, maybe the answer is yes. The methodology available so we can implement our own solution.
Well, no, this plugin was made specifically for QGIS. There was a need for it, and it's not available for ArcGIS. And also, we do not work with ArcGIS here for the workshops we organize, because, well, it's not open source, it's not free. So we have tried to avoid such software, such tools. And if there is a methodology to implement, I mean, the plugin, it's a little tool, it's a code. So I guess if you're really good in coding and like creating plugins, you might do that, but it is not available, like it's not publicly available, the code. The plugin itself is available. Yes, you can have it. You can download it from the website and use it, but, well, the code is not available.
Okay. Well, thank you again for your presentation, Daria, and thanks everyone for your questions. For any unanswered questions, you'll find the answers in the post-event report. Thank you, Daria. We will now move on to our last tutorial, which is an art tutorial that will be presented by Simon Millet. Simon, the floor is yours.
Yes, I will share my screen. Do you see my screen?
Yes.
Yes, okay. Hello everyone, and welcome to this Copernicus Marine Service practical session in air on the dynamic and impact of the Amazon River plume, especially in June 2021. So my name is Simon Millet, and during this session, you will have a closer look at some CMMs product, their structures, format, variable, and how to explore and plot them. So first, we will exploring the NetCDF file. Then we will make a basic plot. Then we will create an animation to see the evolution of the Amazon River plume. Then we will see the chemical loads. Then we will study the movement of the plume via surface current. And finally, we will see the evolution of salinity in water column. So this training focus on the Amazon plume in June 2021. So the Amazon was an exceptional flooding, resulting on high river discharge and a large freshwater plume spreading into the ocean. And this plume is arranged with suspending sediment and nutrients, such as nitrates, phosphate, extending the hundreds of kilometers offshore that impact ecosystem balance along the coast. So this training we allow to see the evolution of different parameters like attenuation coefficient, nitrate, surface current, and salinity over time. So first, the notebook will be set up with all necessary libraries. So here it is all the libraries. There is ggplot2, it is for creating graphic. Dplar, it is for manipulating data. AirColorPowers, it is for color palette in plot. NetCDF4, it is a library for NetCDF file format. GridExtra, it is a library for arranging multiplot on a page. LuberDate, it is a library for datetime data. Skulls, it is a library for aesthetic option. GeoQuiver to create a quiver plot, and Magic, it is for image processing, especially for the GIF format. So first we select all the libraries we load. And if you are using another support, you can install all the libraries thanks to this link here. So in this training, we will use 3 different datasets. There is global ocean physics reanalysis, global ocean biogeochemistry in CAST, and global ocean color. So the 3 datasets are already downloaded in the folder here, data. But if you want, you can try to download. So you can go to the Copernicus Marine Data Store. You have a link here. You can explore all the products available with many filters and the parameters that you want to study. So during this training, we'll focus on the 3 datasets, especially for June 2021. And all the products are daily mints. And if you want to download it, you need your Copernicus Mind credential, username and password. So first we will see the netcdf file. So first we select the path of the netcdf file. Then we open the netcdf file, and we can see all the variables that the characteristic of a netcdf file. So there is here 4 variables. There is 3 dimensions, time, latitude, and longitude. And here it is the global attribute of the netcdf file. So first we load the variable that we want. So latitude, longitude, time, and the KD parameters, that is the diffuse attenuation coefficient. It is possible to see the dimension of the variable thanks to the function dim and the variable, or to see the value for one longitude, one latitude, and one latitude. Here the value. It is possible to do the same with time, but we can see the time here, it is a number, not a date. So to convert the number to a date, we use this function as POSIX, and we put the origin. Here it is in January 1970. The origin, it is noted in the dataset here. So we can see now it is a date. Here to save memory. And now we will make a basic plot of the attenuation coefficient. So first we determine the figure size here, and then we create a data frame dependent only of longitude and latitude because we define the index of time. Here it is the first index of time. And we can see the data frame here that dependent only on the longitude and latitude, and you have a value of the attenuation coefficient. Here there is a whole none because it is on the land, not on the sea. So now we will create the plot. So first we create the folder figures here. If it is not created, it is created. And then we create the figure with the function ggplot. we use GeoRaster to put the data. So with the data frame here, we put the longitude and latitude and the value of the attenuation coefficient. Here it is for color scale option. And here it is general aesthetic option. Here the title and subtitle. Here for the size of the text. Here it is for the adjust the size of a color bar, and here to maintain the proportion. And finally, we save the figure in the folder of figure here. So we can see the figure, so the diffuse coefficient, the KD value, that is an optical indicator that measures the rate at which light is absorbed and scatters as it enters the water. So the plume is clearly visible here, and it moved to the northward along the coast. And a higher value of KD value, which indicate a reduced light penetration in this area, so the plume of the Amazon. Now we will plot different dates to see the evolution of plume. So first we select the date. And then we will make a loop for each date. So here we have the loop, and we select first the index of the time, and then we create a data frame with the index, and then it is the same code that you have seen before to create the map. And we can see the Amazon plume for different dates here. And we see an evolution is clearly visible, and the plume intensity in the 14th and the 15th of June, and then decrease. You can see here, and you can see that the plume move northward along the coast too. So it is not practicable to see the difference of Amazon plume. So now we will create a GIF animation to see clearly the difference of the movement of the plume. So first we select the image that save here in figure for GIF here. And we sort all the figure of the date of creation. And here we can see it is in good order. And then we join all the image and load in the GIF animation. And here you can see the movement of the plume. It is the same conclusion that we have seen before because it is the same image, but it is easier to see the evolution. Now we will we have seen that Amazon plume has different features and vary over time. We now want to investigate which chemical components are transported within the plume. So first we load the second dataset. We have the characteristic of the dataset here, and we load all the variables that we want. And here it is to verify the date is correct. And then we search the index of the different time here to plot the map. Here we create the function for plotting map. It is to avoid to have 4 times the same code. It is easier, but it is approximately the same code that you have seen before. And then we create with the function mapping the maps that it is in variable P1, P2, P3, and P4. And then we create an image with 4 figures with 2 columns and 2 rows. And then we save in figures. And we can see the concentration of nitrate here. And we can see that the concentration of nitrate closely follow the shape of the plume that we have seen before. This indicates that the river plume transports a significant amount of nitrate, which has a substantial impact on marine chemistry and biology, especially along the coast. So now we have seen that the plume transport several chemical substances. You can try other substances if you want, such as ammoniac or dissolved oxygen if you want. We will now examine how the plume direction evolve under the influence of a surface current. So first we load the third dataset and we load all the variables, the same code that you have seen before. And then we select the index for this date to see the influence of the data of the current. So first we create the data frame here. And then we create a second data frame, especially for plotting the arrow on the map to see the direction of the current. It is based on the original data frame, so this one, but we reduce the number of points to make the arrow visualization clearer. So we choose a step of 0.25 degrees. Here the round, and then here the df space. It is originated of the data frame df, but with reduce the number of points. And now we plot the maps. So we use ggplot with the data frame, and we add the current geom-time, and we add a vector display. So we geom quiver. We will use the df space here. And we can see the current here. And so we have just a visualization of one date on June 15, but we understand why the plume extending northward following the coastline, because the current is on the same direction. So if you want to, you can try over date to really see the evolution of a plume and correlate with the current. And finally, we will see the evolution of salinity in water column. So we have seen, we will examine the water salinity across different depths, so between 0 and 20 meters, in order to assess the mixing caused by the plume. So first, we select the coordinate of a point that we want to study, because we will study only on one point. Then we will create vertical interpolation, and finally we plot the figure depending on time and depth. So the point that we want to study, it is this one. So we select the nearest coordinate of the dataset. So it is this one. So it is very near of the coordinate that we want. And then we create a data frame. So dependent here of the depth and time, because we select the index that we have find here. And we can see the data frame that depends of the depth, of the time, and varies the salinity. And now we will create a a regular vertical grid to avoid the blank when we plot the map. So we create a vertical grid each 1 meters, and then we interpolate the value of this data frame each 1 meters. And we can see here the time and the depth each 1 meters and the salinity value. Then we set the start and the end date, and we filter with the date. And here we plot the figures. We use ggplot. We put the data frame, the time and the depth, and the salinity values. I see approximately the same code, and you can see here the C salinity dependent of the time, the date, and the depth here between 0 and 20 meters. And this figure show a sharp decrease in sea surface salinity, especially here on June 15. So between 0 and 5 meters, corresponding to the period when the plume was it was its maximum extent. So it is for this the salinity is very low at this period. So this training is now finished. So thank you for your attention, and if you have some questions, do not hesitate. Maybe there is some problem with the question.
So,
Okay,
wait, sorry. My Zoom just crashed,
no problem.
but I'm back. Um, Thank you for your presentation, even though I haven't heard the end of it. I don't see any question for now in the Slido. So if you have any question, don't hesitate to post them on the Q&A tab, and they're slowly starting to come. For the first question, is the code for salinity in R publicly available?
Yes, the code will be available in the page of event, and the salinity value are available in CMM's product, where you can download it the dataset.
Okay, nice, thank you. Can it be used to determine potential fishing ground areas?
Yes, it is possible because we know that the fishing areas are where there is river transport different polluant, but there is many nutrients, and fish lack this best region. So it is possible to know some area for fishing.
Okay, nice. Can we use it to determine the effect of erosion?
I think it is difficult. Here we see the pollution of Amazon, but the erosion it is more difficult. But we can use different another data set, things like waves, but we didn't see the erosion, but we can see the impact of a wave on the coast.
Yes. Okay. What is the right format to import the data set in R?
I use a netted file format. It is the most easier, and it is the format that it is available in Copernicus Marine Service.
Yes. Can we merge multiple data sets into a large one?
Yes, it is possible. There is many function and libraries are available in R. So there is some libraries I don't have the name, but it is possible to merge multiple dataset in one.
Okay, nice. Can the MyBinder environment be used following the training to work with the data and notebooks? If so, how long will it stay running?
So ouais.
Yeah, go on if you have a...
The MyBinder environment, it is the environment that the Copernicus Marine Service use. There is a whole library that we need for this training. Um, and I don't know how long will it stay running. Maybe you know, Florian?
Yeah, I think it's 2 weeks or 14 days. But once this time is over, you can also run it locally on your computer and through the Binder Hub.
Okay.
For the next question, what are some unique pros of using R for this data instead of Python or in QGIS directly?
Um, R is very good for statistic um, statistics um, study. Python are more used in the community, and there are more and more libraries and functions that permit to do the same with R. And QGIS I don't use, but it is very um, useful for to see a map and to see map. But the three different code is very useful to see Siemens product, and we have seen in this free tutorial of the different cases to use the Siemens product.
Okay. Yeah, the next question is also a bit the same to
The
know
same, yes.
how application would be better. And is there any way we can download CMS Copernicus Marine Service data using R? And
I
there will be a link in the chat also.
yes, I don't know. I don't think, but you can ask the question at the user support. But I download the Siemens data thanks to the Copernicus data store, and then put on my Jupyter Air at my Jupyter Air notebook.
Okay, nice. Yeah, we'll find a bit more information on this in the chat. Thank you very much, Simon, for your presentation and for answering our participants' questions. We
Thank you.
will now slowly close the webinar. Just a reminder that all the tutorials that were shown today are available on the event webpage. You will find them in their dedicated section, and we encourage you to take some time after this session to run the tutorials on your own at your own pace. You can also find all previous tutorials developed for other trainings on the Copernicus Marine website in the e-learning materials. So you'll be able to explore step by step other products from the catalog and get better at coding for those of you who need it. One last reminder about replays and polls. So you'll also find both of these on the event website through the menu at the top of the page. We will also send you an email to let you know when the replay is available and a link to the poll about today's webinar. If you can fill it, that will be very helpful for us. If you'd like to go further after today's session, I encourage you to visit the Copernicus Marine Service YouTube channel, where you'll find a rich library of webinars and training sessions from the past few years, all freely available. Each video focuses on a specific theme, whether a region of the world, a blue economy sector, or a practical example of how ocean data supports real-world applications. So it's a great way to deepen your knowledge at your own pace and explore use cases that match your interests. You can also discover all Copernicus Marine events, both upcoming and past, via the Events tab in the top right menu of the website, where you can open any event page for details and registration. Thank you for joining today's session. We hope you find the presentations and tutorials insightful and that you discovered new ways to use the Copernicus Marine Service data to address water pollution challenges. Before we wrap up, I'm happy to invite you to our next webinar, which will take place on January 13th at 10 a.m. CET. This upcoming session will be a 2 hours hands-on workshop during which we'll go step by step through an in-depth Python tutorial using CMS data. This time there will be live exercises that you'll be able to follow on your own computer directly alongside the trainer. However, please note that the number of available tickets will be limited, so we encourage you to stay tuned for the registration announcement and secure your spot as soon as possible. We look forward to seeing you there. Have a nice day or evening, and see you soon.
Bye.